influences on climb performance. When surveying the various factors that affect climb performance and the choices made by pilots as they gain altitude, both during takeoff and while the aircraft is already in flight. The weight of an aircraft has a significant impact on aircraft performance. For example, an increase in weight means that the angle of attack, also known as AOA, must be higher in order to maintain altitude. Greater weight diminishes reserve power, lowers the climb rate, diminishes the maximum rate of climb, and increases drag. So, the maximum rate of climb, for example, of a plane increases as the weight decreases, and the weight of a plane will decrease as it burns off fuel over the course of a long journey. And so, at the end of a long journey, a plane will have a higher maximum rate of climb. The climb performance of an aircraft is affected by certain variables. The conditions of the aircraft's maximum climb angle or maximum climb rate occur at specific speeds, and variations in speed will produce variations in climb performance. There is sufficient latitude in most aircraft that small variations in speed from the optimum do not produce large changes in climb performance, and certain operational considerations may require speeds slightly different from the optimal. Of course, climb performance would be most critical with high gross weight at high altitude, in obstructed takeoff areas, or during malfunction of a power plant. Then, optimum climb speeds are indeed necessary. Weight has a very profound and pronounced effect on aircraft performance. If weight is added to an aircraft, it must fly at a higher angle of attack, or AOA, in order to maintain a given altitude and speed. This increases the induced drag of the wings, as well as the parasite drag on the aircraft. Increased drag means that additional thrust is needed to overcome it, which in turn means that less reserve thrust is available for climbing. Aircraft designers go to great lengths and effort to minimize the weight of an aircraft, since it has an effect on the factors pertaining to performance. A change in an aircraft's weight produces a twofold effect on climb performance. First, a change in weight of an aircraft will change the drag and the power that is required. This alters the reserve power available, which in turn affects both the climb angle and the climb rate. Secondly, an increase in aircraft weight will reduce the maximum rate of climb, but the aircraft must be operated at a higher climb speed in order to achieve the smaller peak climb rate. An increase in altitude also will increase the power that is required and decrease the power available. Therefore, the climb performance of an aircraft diminishes with altitude. The speeds for maximum rate of climb, maximum angle of climb, and maximum and minimum level flight airspeeds vary with altitude. As altitude is increased, these various speeds finally converge at the absolute ceiling of the aircraft. At the absolute ceiling, there is no excess of power, and only one speed will allow steady, level flight. Consequently, the absolute ceiling of an aircraft produces zero rate of climb. The service ceiling is the altitude at which the aircraft is unable to climb at a rate greater than 100 feet per minute, or FPM. Usually, these specific performance reference points are provided for the aircraft at a specific design configuration. And in discussing performance, it frequently is convenient to use the terms power loading, wing loading, blade loading, and disc loading. Power loading is expressed in pounds per horsepower and is obtained by dividing the total weight of the aircraft by the rated horsepower of the engine. It is a significant factor in an aircraft's takeoff and climb capabilities. Wing loading is expressed in pounds per square foot and is obtained by dividing the total weight of an airplane in pounds by the wing area in square feet. It is the airplane's wing loading that determines the landing speed. Blade loading is expressed in pounds per square foot and is obtained by dividing the total weight of a helicopter by the area of the rotor blades. Blade loading is not to be confused with disc loading, which is the total weight of a helicopter divided by the area of the disc swept by the rotor blades.